We're going to continue our study on probability today, and we're going to go over some more what we call basic concepts of probability. The first basic concept is what we call the union rule. So if you have two events E and F from your sample space S, then the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersected with F. Really, this is just an extension of some set theory where we talked about how if you count all the elements that are in one set and add them to all the elements in the other set, if there is an overlap, then you've double counted everything that's in the overlap and you'll have to subtract that out. So that's exactly what's happening here. So the probability of E plus the probability of F minus the part that you double counted, which is E intersected with F. Let's take a look at an example of this. If a single card is drawn from an ordinary deck of cards, find the probability that it will be a red or a face card. Now what we're going to do is we're going to go ahead and apply that union rule here. So the probability that you will draw a red or face card, so R union F, is equal to the probability of drawing a red card plus the probability of drawing a face card minus the probability of drawing a card that's both a red card and a face card. Now this actually, you might not need to use the union rule. We're just using it here so you can see very clearly where the overlap is and understand how it's actually subtracting out what you don't want. So we have the probability of a red card, which is going to be, well, 26 of the 52 cards are red, plus the probability of a face card. Now we know that there are 12 face cards, so 12 over 52. And then the probability of choosing a red and face card, there are 6 of those. So minus 6 over 52. So you'll notice that when we counted up the 26 red cards and then we counted up the 12 face cards, there were 6 cards that overlapped. And that's exactly what we're subtracting out here. So this ends up being 32 out of 52. And if you simplify that, that comes out to be 8 over 13. Next, we have what we call the complement rule. So the complement rule states that the probability of E, some event E, is equal to 1 minus the probability of E prime, so everything that's not in E. Same thing the other way around. So the probability of E prime is equal to 1 minus the probability of E. Now this may seem like an obvious thing, where if you're trying to find the probability of some event E happening, you know that is equal to, well, everything that's not inside that set. If you subtract that from 1, that's going to give you the probability. Now, the complement rule is typically easiest if, say, it's easier to find one or the other because there are fewer things to count, and then all you have to do is subtract. So let's take example 2 as an example of this. If 2 fair dice are rolled, find the probability that the sum of the numbers rolled is greater than 3. Okay, now we're looking at 2 dice. So let's talk about what the sample space is. Well, we have to come up with all the different possibilities that you could get. You could have a 1 and then a 1, a 1 and then a 2, a 1 and a 3, all the way up to 1 and then a 6. And then let's account for if the first dice was 2 instead. So 2, 1, 2, 2, 2, 3, all the way up to 2, 6. And we continue this until we get up to 6. So you can see here we have 36 different possible outcomes. And now we're trying to find the probability that the sum of the numbers rolled is greater than 3. Now, I think it's actually easier to find how many of these, or count up how many of these, have a sum that's less than or equal to 3. Now, that would be these 3 here, and everything else is going to add up to be more than 3. So you know everything else is going to help you figure out the probability that the sum of the numbers rolled is greater than 3. So you can either add everything else up, or you can do what I'm going to do here, which is make use of that complement rule and find the probability that the sum is less than or equal to 3. So that's really the E prime that we're finding here, and that's 3 out of 36, which is 1 over 12. Now I know the probability that the sum is greater than 3 has to be equal to 1 minus the probability of our e prime here, which is the sum is less than or equal to 3. So this is simply 1 minus 1/12, and we know that's equal to 11 over 12. Now obviously you can absolutely count up all the other outcomes, and that would give you 33 out of 36, and that would still leave you with the answer 11 over 12. But just as an example, so that you can see how we can use the complement rule to help us more easily find our probabilities, this is an example of it. I only had to count up 3 and then subtract it from 1. Now another thing that you'll encounter when we're talking about probability is actually odds. Now odds are a comparison of the probability of some event occurring and the probability of that event not occurring. So the odds in favor of an event E are defined as the ratio of P of E to P of E prime. So you would put P of E on top and P of E prime on the bottom. Now the probability of E prime cannot equal 0. It is absolutely possible that E prime is equal to 0, so just be aware of that. Now if the odds favoring event E, if they are M to N, then you can translate them back into probabilities. So the probability of E occurring is going to be M over M plus N, and then the probability of E prime occurring is going to be N over M plus N. So those are the two things that you need to know, how to go back and forth between odds and probability. And typically when you're talking about odds, you're talking about what's the ratio of this happening to it not happening. But probability, it's always the ratio of this happening to all the different possibilities. Take a look at example 3. Suppose the weather forecaster says that the probability of rain tomorrow is 1/3. Find the odds in favor of rain tomorrow. Alright, so we're trying to find odds. So I want to find the probability that it rains and put it over the probability that it doesn't rain. Now just so that we have some notation going on here, I'm going to call E the event that it rains tomorrow. Now I want to find the probability of E over the probability of E prime. Well, what's the probability that it rains tomorrow? That's 1/3. What's the probability that it does not rain tomorrow? That's 2/3. And dividing those, we end up with 1/2. So the odds in favor of rain tomorrow are 1 to 2. So remember, odds are always the probability of that happening to the probability of it not happening. Let's look at an example where we are given the odds and we have to come up with the probability. So the odds that a particular package will be delivered on time are 25 to 2. Find the probability that the package will be delivered on time. Again, remember, odds are always the ratio of it occurring to it not occurring. So 25 to 2, we want to translate that back into probability. So you can say 25 is M and 2 is N. So the probability of the package being delivered on time is going to be M over M plus N, so that's 25 over 25 plus 2. So that's equal to 25 over 27. Again, probability is always the ratio of the event occurring over all the possibilities of what could happen, whereas odds, the 25 to 2, is the ratio of the probability of it occurring to the probability of it not occurring. Look at part B. Find the odds against the package being delivered on time. Now here you're not asked to find a probability, you're asked to find odds. Now you are already told the odds that it being delivered on time are 25 to 2. Now you just want to write what the odds are against the package being delivered on time. So all you have to do is just swap the 25 and the 2. So this is 2 to 25. So the odds against the package being delivered on time are 2 to 25. Alright, the last thing we're going to talk about today is what we call probability distribution. So a probability distribution is simply a table that lists each possible outcome of your experiment, and the corresponding probability is what we call a probability distribution. Now, the probability of each outcome, because we are talking about probability, has to be between 0 and 1. Secondly, the sum of all the probabilities that are within your probability distribution, within your table, all of those should add up to 1. So take a look at example 5. The following table lists U.S. advertising volume in millions of dollars by medium in 2008. So we have the medium, television, magazines, newspapers, internet, radio, outdoor. And then on the right, we have the expenditures. This is in millions of dollars. Now it says in part A, construct a probability distribution for the probability that $1 of each advertising is spent on each medium. So what you need to do here is you want to come up with the probabilities, but before we come up with the probabilities, you're going to need to know what the total expenditures are. So go ahead and add all of those expenditures up, and that totals to $141,968. This is in millions. All right, now we want to come up with a table that lists each probability. So what we're going to have to do is we're going to have to take each expenditure. So say you're looking at television as the medium. The expenditure is $65,137. In order to write the probability distribution, we have to put this number, $65,137, over the total expenditures, $141,968. That comes out to be about 0.4588. And then we do that for the entire table. So magazines, 28,580, put that over the total. That comes out to be 0.2013, and so on. Now you'll notice that all of these probabilities that we've come up with are between 0 and 1. And if you were to add all these up together, that should add up to 1. Now if it doesn't come out to be exactly 1, the reason is because we have done some rounding here. We rounded to 4 decimal places, which is pretty good, but it might still not add up to exactly 1. All right, so part B, find the probability that $1 of advertising in the United States is spent on newspapers or magazines. All right, so newspapers, magazines, we can look up in the table that we just created what the probability of each of them would be. So to find the probability of it being newspapers or magazines, all you have to do is add those two together, and that comes out to be 0.3778. Now in this case, we don't have to worry about double counting anything because there is no expenditure that is on both magazines and newspapers. There's no overlap here. So since these are what we call disjoint sets, we just have to add those two probabilities together. There's nothing that has been double counted.